Okay, so we're doing the integration of exponentials with this video. Should be pretty easy since the derivative of an exponential is itself. Of course, just watch out for doing chain rule. The integration of an exponential is going to be itself, and of course, we're just going to have to watch out for anything that's going to kick out with U sub. If I'm just integrating e to the x, well then it's just e to the x plus c. In general, if it's e to the u, we've done the U sub work. The integration of e to the u is just e to the u plus c. You just worry about what kicks out because of the U substitution. Let's do a little quick example quickly. If I have something like e to the 2x, if I was taking derivatives of this, right, the first derivative would be 2 e to the 2x. The second derivative would be 4 e to the 2x. Then it would be 8 e to the 2x. Right? Every time I take a derivative, you would just keep having another 2 that would kick out to the front because of the chain rule. Now, if I was integrating, so if I was integrating e to the 2x, your u would be this. So that means the derivative is supposed to be a 2. That means if I integrate it, you would actually kick out a 1/2. And I would have a 1/2 e to the 2x. And then if I integrate it again, I would have a 1/4 e to the 2x. And if I integrate it again, a 1/8 e to the 2x. And then again, I would have a 1/16 e to the 2x. The exponential part itself should never change, whether you're doing a derivative or an integral. You just worry about what's going to kick out to the front. For a derivative, you find the chain rule derivative, right? You find the derivative of that piece, and then that multiplies to the front. For an integral, you find the derivative of that piece, and then it divides to the front. That's really all U substitution is, okay? Right? Instead of that chain rule piece multiplying to the front, it's going to divide to the front. All right, so there we have it. If you had something also, like how about if I had e to the x over 3? If I was taking derivatives, you would have a 1/3. Am I on the screen? I'm not really. If you had an x over 3, you'd have a 1/3 e to the x over 3. Then if I took another derivative, it'd be a 1/9 e to the x over 3. Then a 1/27 e to the x over 3, right? If the chain rule part, right, here that chain rule part, previously the chain rule was a 2, so the 2 would multiply to the front for derivatives, the 2 would divide to the front, creating fractions for the integrals. Here, the chain rule part is 1/3, so that 1/3 is going to keep multiplying to the front. So you're actually going to keep kicking out these fractions. Every time I take a derivative, another 1/3 multiplies down to the front. But here we go. If I was integrating e to the x over 3 dx, right? The chain rule derivative of this would be 1/3. Instead of instead of that 1/3 multiplying to the front, you divide by it. But if you divide by 1/3, that's the same thing as multiplying by 3. So if you were to integrate this, the chain rule derivative, 1/3, would divide to the front, and if you divide by a fraction, remember, it's the same thing as multiplying by the reciprocal. If I were to integrate again, you would just kick out another 3. If I were to integrate again, you would just kick out another 3. The exponential part would never change. You just worry about what kicks out to the front because of the chain rule, or what kicks out to the front because of the U substitution, basically for the chain rule. You find the derivative of that piece, and then that chain rule derivative is going to multiply to the front for your derivatives, or if you're integrating, that chain rule derivative piece is going to divide to the front. Sometimes you kick out whole numbers, sometimes you kick out fractions, and that's going to change based on whether you're taking a derivative or whether you're integrating, and it's going to change on whether your u was a fraction or whether it was a whole number. But the exponentials should, I think, be pretty easy either way. Just worry about chain rule when you're taking a derivative, and then correspondingly worry about U sub when we're doing an integral. Here, if you wanted to write out this work, the u would be 3x plus 1. I'm not on the screen. Let me fix that really quick. So here for this first example, we would set the u as the exponent. It's always setting the u as the exponent. The derivative would be a 3 dx. Since you're missing the 3, the U substitution just tells me you're going to kick out a 1/3. So here I would have a 1/3 e to the u du, which integrates 1/3 e to the u plus c. And then you would just reverse substitute back 1/3 e to the 3x plus 1 plus c. Remember, you could always check your indefinite integrals by just taking the derivative. It's going to work. Just worry about what kicks out to the front because of the u sub. Okay, let's do the next one. If you need to, the 5, you can just factor it out to the front, and you set your u as negative x squared. So the derivative is negative 2x dx. You have the x, which is good. If that x was missing, we would have a problem, and we wouldn't be able to integrate. But we have the x, we have the dx, we're missing the 2, we're missing the negative. That's okay. A negative 1/2 kicking out to the front explains why the negative 2 is missing. Don't forget about the 5. So if I have the 5 out in front, and I have this negative 1/2, I have a negative 5/2. E to the u. Oops, du. I was trying to go too far. And then the integration of e to the u is going to be negative 5/2 e to the u. I'm going to reverse substitute, plus c. So these exponentials are supposed to be pretty easy. Hopefully you agree that they are. If not, just put in some practice, and hopefully they will become easy. This next one, you may benefit from rewriting it. You have e to the 1 over x, but instead of writing it as divided by x squared, you could write that as times 1 over x squared dx. And that may help you see that here's the u, right? The exponent is still the u value. Now that's a reciprocal. That's x to the negative first. So if you take the derivative, that's going to be negative 1 x to the negative second, so the derivative would be negative 1 over x squared. So here's my u. The derivative of it almost matches, right? It almost matches perfectly. The only thing that it's missing is the negative. Okay, so that one's going to be a negative e to the u du. So that means it's going to be negative e to the u plus c. So that's negative e to that 1 over x plus c. The better you are with the derivatives, like if you can just see, why is this x squared on the bottom, or why is this 1 over x squared on the right? The better you are with derivatives, you'll just know, like, hey, the derivative of that, it's pretty close to matching that extra stuff, right? That kind of helps you see how this u sub is going to tie together. The better you are with the derivatives, typically the easier the integrations will be. Like here, why do I have this extra sign? Well, because this chunk is a cosine. And if your u is cosine, your derivative, it's supposed to be that extra sign. Now, the derivative of cosine is negative sine. So in a perfect world, this would have been a negative. But we can live with the negative not being there. If that sign was not there, and if it was just e to the cosine, that would be a non-integrable function, and we wouldn't be able to integrate it. But since the sign is there, that means the u sub will all fit together. The fact that it's off by a constant, no worries. This one is just the negative e to the u, which once again will integrate into negative e to the u plus c. So I'm going to have negative e to the u plus c. So negative e to the cosine x plus c. I kind of skipped that middle step just because I was lazy. I literally did. It's right here, right? This is the same thing. Right, this would have been right here. Then I reverse substituted. Alrighty, let's do a couple more. Okay, let's look at this next example. I see I've got this division, and I'm like, oh gosh, okay. If I set u as the top, the derivative would be e to the x. Ooh, that almost matches the bottom, but not quite. Let's try to set u as the bottom. So if I set u as e to the x plus 5, the derivative of it would be e to the x plus 0, and then dx. Oh, so look, that matches perfectly. You typically would want to set the bottom as u. And then here I end up having 1 over u du, which if you remember, just back like 2 days ago, that's just the integration of ln of u plus c. And then I would have ln of e to the x plus 5 plus c. Now, sometimes I like say something that's not quite always 100% accurate. Remember, I say if the e and the ln are right next to each other, they'll cancel, but that's not always true, right? If you had e to the ln of something power, those would cancel, and if you had just an ln of e to the x, that would cancel, leaving just the x. But here, since I have that addition first, that would actually come, like all this stuff that's in the parentheses or that's in the argument, that would come before doing your exponential or doing your log. So that e and that ln, even though they're written right next to each other, they would not cancel. deal, because I could just as easily flip that order and the 5 would be in between. Okay, so if you have multiple chunks in there, don't cancel the e with the ln, right? That's as simplified as it's going to get. Even though the e and the ln are right next to each other, they don't cancel because you have that extra chunk, the plus 5. And that would happen first since it's inside that operator, the parentheses or the absolute value. Absolute value operates at the same stage in your PEMDAS as your parentheses. It's just kind of like PEMDAS would sound weird if you had like P and then AV, right? PVM is too complicated to say, right? PEMDAS is easier, but the absolute value would be done at the same stage as your parentheses. Okay, the next one, we would look at it, and we would try to think, okay, if I set u as the top, the derivative would be 7e to the 7x plus e to the x. We'll see if it matches. Oh, no, not even close, all right? So then let's try to set u as the bottom. The derivative would be 3e to the 3x. We'll see if it matches. Oh, no. Oh, it doesn't even match at all. Okay, so U substitution doesn't work because the top is not the derivative of the bottom or anything close to it. So instead, you just have to algebraically split this up and then simplify it. Since this denominator is only one piece, it is okay to take that fraction and split it up. And then since these exponentials have the same base, you could reduce it. Just like if I had x to the 7th over x to the 3rd, we know that would be x to the 4th. This is going to also be the same thing, right? When you have the same base, what you do with those exponents, you subtract them. You know that rule. Don't mess it up because it's an exponential now. Here, this is all going to simplify, and you're just going to have e to the 4x. 7 minus 3 is 4x. And then here, that's going to be e, but there's 2 on the bottom. So then that would be plus e to the negative 2x. So this one starts as that quotient, but there is no quotient rule. Some quotients we can do with U substitution, but that doesn't work here. So instead, I have to algebraically simplify it. And then once I have it algebraically simplified, now I could go through and I could integrate. If I was taking a derivative of this term, the 4 would multiply to the front. Since I'm integrating, that 4 is going to divide to the front. So the integration of e to the 4x is going to be 1/4 e to the 4x. And then here, this negative 2 is going to divide to the front. So it's going to be a negative 1/2 e to the negative 2x. Just think, what's the chain rule part? What's the derivative of that exponent? And if you're taking a derivative overall, that chain rule part would multiply to the front. If you're integrating, that chain rule part would divide to the front. Alrighty, let's move on to the next one, which is a definite integral. I'm not going to do the U substitution work. I'm just going to do it, right? It's going to be 1/3 e to the 3x plus 1. Right? That's easy. It's supposed to be 3. It's not there, so 1/3. That's easy. 1 to 3. Let's plug it in. So we're going to have 1/3. I have e. Let's plug in 3. 3 times 3 is 9. 9 plus 1 is 10. Minus 1/3. 3 times 1 is 3. 3 plus 1 is 4. You could factor out the 1/3 if you wanted to, and have e to the 10th minus e to the 4th. Could I go any farther? Could I write this as 1/3 e to the 6th? Just think to yourself. If you think it will work with e's, ask, does it work with x's? Is x to the 10th minus x to the 4th, is that x to the 6th? No, those are not like terms, so you cannot combine them. The same thing happens with the e's, right? Your rules of algebra still apply. The fact that it's an e instead of an x doesn't matter. Okay, that doesn't simplify any farther, but I would have a lot of students who are going to tell me that that's e to the 6th. That's not right. Sorry, go back to algebra. All right, the next one, we would do the U substitution. Here's the U. The derivative of it matches perfectly, right? So I can see it's just 1/u du, right? Here's the u. It matches perfectly, so I don't need to kick out anything. So it's going to integrate, and it's going to be ln of u. It's going to be ln of 1 plus e to the x. And then psi, because this is a definite integral, which means I have to evaluate. Okay, so now I'm going to plug in the 1. E to the 1 is just e, so I have ln of 1 plus e minus, if I plug in 0, e to the 0 is 1. 1 plus 1 is 2. So you could leave it like this, That's not terrible. If you wanted to combine it, you could. Since you have the same base, you have that same natural log, you could combine it. That one's subtraction, though, so you'd have 1 plus e divided by 2. I don't know. There's really no benefit to having it like this over this, but if it was a multiple choice question, we would have to recognize that, hey, if I get that, but that's not one of my answer options, but that is, we would just have to recognize that they're the same thing, right? So U substitution, that one matched perfectly. How lovely. Same thing with the next one. All right, so that was my U. The derivative of it matched perfectly. Here's my U for the next one. The derivative of it matches perfectly. So here, this is just the integration of cosine of u du. And then the integration of cosine is sine. So I'm going to have sine of u, reverse substitute it. And then we can go back to x. So I could go back to having the x limits. And then we can plug it in. So I'm going to have sine. Let's plug it in. E to the 0 is 1 minus sine, say e to the negative 1. And then that's it. There's really nothing else we could do. I mean, if you wanted to, you could rewrite this as sine of 1 over e. But either of those is as good as you can get. That doesn't simplify any farther. Those don't combine because what we just did, right, that was a property of logs. That's not a property of sines. So something like this or like this, that's as good as you could get that answer. Alrighty, next one. If I'm going too fast, remember, the magic of a video is you can always pause it, go back and rewatch it if you need to. But I'm kind of tired of doing these notes, so I'm going to go a little bit faster. Solve the differential equation. That means tell me, what does y equal, right? That's what it means, solve the differential equation. It gives me the derivative. It's asking, what's the original function? We've been doing differential equations for a while. In the next note packet that we do is going to have a lot more of them. But solve the differential equation means tell me what is y equal to. What's the original function that meets this specific derivative? So here I know I'm going to have to integrate the derivative. So let's integrate x squared e to the x cubed. I'll actually write out the u sub work this time because I've been a little bit lazy. The u would be the exponent, x cubed, and the derivative would be 3x squared. I have the x squared, but I'm missing the 3. Oh darn. That just means a 1/3 would kick out. So I have a 1/3 e to the u du, and then the integration of e to the u is just e to the u. I'm going to reverse substitute, and then plus c. There's your original y equals. That's the solution. That's the equation that would have this for the derivative. Now remember, if I had any piece of information, like if it said, hey, like y of 0 is 5, then I could use that to solve for the c value, and I could get the particular solution. But since I don't have that, this general solution is the best that I can do. Okay, 3 more examples, and then we're going to be done. So here it says, speaking of finding that particular solution, it says here's the derivative, and here's a piece, right? Sometimes it'll write it out like this. Most of the time it will. Other times it'll just give you a coordinate point. That's okay. It's the same thing. But it says here's the derivative, find the particular solutions. We're going to integrate, use the condition to solve for c, plug it in. Alrighty, let's go for it. Now, if I integrate, it'll be a 1/5 e to the 5x. Remember, the chain rule derivative would be 5. That 5 divides to the front, since we're integrating. The integration of a sine is negative cosine plus c. Remember, just take the derivative. The derivative of this should match what you started with. If it doesn't, you integrated wrong. But it does match, because I'm pretty good at this. Right, so now let's go through and use the condition. We got f of 0 equals 3/5. Therefore, 1/5 e to the 0 minus cosine of 0 plus c is going to be equal to 3/5. E to the 0 is 1. It doesn't cancel. It's just 1. So I've got 1/5 minus cosine of 0 is also 1 equals 3/5. So let's see. 1/5 minus 1. So that's a negative 4/5 plus c equals 3/5. So add the 4/5 over, and I've got c is going to be equal to 7/5. That's not the answer. The answer is going to take that and then plug it back in. So my answer, f of x, is going to be 1/5 e to the 5x minus cosine of x, and then plus my c value having been plugged in. That's the answer. Okay, integrate, use the condition to solve for C, plug in the C value, and then there's your particular solution. Remember, your general solution sometimes is as good as you can get, but if you have a piece of information, you should and you can use it to find for that C value, and then plug it in. All right, let's look at the next one. It says find the particular solution. It starts me with the second derivative, so I'm going to have to integrate twice. Oh well. It gives me the two pieces of information. How lovely, right? So that's good. Let's go for it. Integrate once to get from f prime up to f. Sorry, to get from f double prime up to f prime. Right? So integrating once. The integration of cosine is sine. Remember, the derivative of sine is cosine, so that checks. The integration of this is going to kick out a 1/3 e to the 3x. Plus c. Okay, so we've integrated once. Now let's use this condition. So I'm going to set it equal to 2/9. Sine of 0 was 0. Plus 1/3 e to the 0 is 1. So that's nice. This piece actually is 0. So I have 2/9 is equal to 1/3. You know what I did? I'm using the wrong one, right? It shouldn't be 2/9. That's f. Sorry. Ooh, at least I caught it now. It should be 7/3. I was like, why is it 9? Okay, so 7/3. That was nice. At least it was still 0 for both. But it should be, since I'm at the f prime level, it should have been 7/3. My bad. Just using this one first and then that one second. All right, so there we go. So we set it equal to 7/3. Still would plug in the 0, so that's still going to cancel. That's still going to be 1. So we have 7/3 is equal to 1/3 plus c. That means my c value is 6/3, aka 2. Okay, so let's plug it in. Now I have this first derivative, but in particular, it's sine of x plus 1/3 e to the 3x plus 2. And now I'm just going to repeat that whole process. We're going to integrate to get up to the original function. The integration of sine is negative cosine. Just check it. Is the derivative of this that? Yep. When I integrate again, it's just going to kick out another 1/3. So I'm going to have a plus 1/9 e to the 3x. The integration of 2 is 2x. Even though we've already solved for the c value and have plugged it in, just don't use c again, right? It's just not proper. Use a different letter. I'm going to use d. Now we can use this condition. I was greedy and I was too eager to use earlier. So now 2/9 is going to be equal to negative. Cosine of 0 is 1 plus 1/9 e to the 0 power is also 1. 2 times 0 is 0, so that's going to cancel. So that's all going to be gone. So I've got a negative 9/9 plus a 1/9 plus d. That equals 2/9. So see, this is a negative 8. And from a negative 8, I need to end up with a 2. So that must have been 10/9, right? Because negative 8 plus 10 would give me the 2. So I've got the d value. It has to be 10/9. And then we'll just go plug it in, right? Here was my original function. And now I can just plug it in. Negative cosine of x. Then I had the 1/9 e to the 3rd, or e to the 3x, so plus 1/9 e to the 3x, plus 2x, and then instead of the d value, plus 10/9. That would be the particular solution that goes through the point 0, 2/9. Right? So sometimes it'll tell you the coordinate points. Really, it goes through this point, and then at that point, it's got to have a slope of 7/3. So it tells me what the coordinate point is, and it tells me what's the slope of the graph at that point. Most of the time, it'll spell it out like this. So you integrate twice, use the two conditions to solve for the constants. So be it. I love it when they ring the bells and there's no students on campus. All right, thank you. I wonder if you guys can even hear that on your end. I don't know. If anyone ever watches the video, which, no one ever does. It's just literally a waste of my time to make them. Someone could tell me if you can hear the bells in the background, because I would guess you probably can. Oh well, just mildly curious. The rate at which water is being pumped into a tank is given by this R sub t function, where t is measured in minutes, and R sub t is in gallons per minute. So it gives me a rate function. It says water's getting pumped in, so I have an inflow rate. And it says how many gallons of water have been pumped into the tank. And it says in the first 5 minutes. So remember, the change in the water. This gives us a good change, right? Remember, the integral of the rate of change is your amount of change. That's your fundamental theorem of calculus at play. The integral of the rate of change, that's an integral symbol, it looks like S-rock. It's the integral of the rate of change is your amount of change. So since I have an inflow function, if I were to integrate it, it's going to tell me how much has come in. So if I want the change in the water, and it says in the first 5 minutes, so that's from 0 to 5, what I would have to do is just integrate from 0 to 5. And if I want the change in water that comes in, I would have to integrate the inflow function. Now you can either write it out or you can name it. Either way, it doesn't really matter. So you have 20 E. Let's see, that would be 2 over 100, so that would be 1 over 50 T. We could do something like that by hand. It would kick out a 50 because of the U substitution. But either way, I think we would use the graphing data calculator and we would just use the Math 9 feature. Could we do it by hand? Yes. If push came to shove, yes, we could do it by hand, but we're going to Math 9 it, and we're going to end up figuring out that change in water, which you get by integrating the inflow rate, right? How much water has come in, you would end up finding at 105.171 gallons. That's the amount of water that comes in. Now, if it told me, like, hey, Mr. Bell, it starts off with, 50 gallons of water, then you would add 50 to that answer to get the final amount. Sometimes you get questions that ask, what's the amount of change? How much has come in? Which in this case it does, so it only wants the integral value, just the change. But other times you'll get questions that ask, how much is in there at the end? So you would either have to take that change and add it to your initial, or you'd take that change and subtract it from your initial. But then either way, you would be able to get the answer. This one just wanted how much has been pumped in, so all I needed was the change, all I needed was the integral. I don't care how much is in there at the end, all I need is just the integral value.